Have you ever wondered how do the laws of physics apply beyond our perception? Today we'll discuss 4 concepts and theories. First, space-time altered regions. This term isn't commonly used in mainstream physics, but it likely refers to areas where the properties of space-time are different from the norm. In general relativity, space-time is the 4-dimensional continuum that combines the 3 dimensions of space with the dimension of time. Altering space-time could involve phenomena like warping or bending the fabric of space-time, as theoretically predicted around massive objects like black holes or in concepts like wormholes. Second, gravity and anti-gravity forces. Gravity is a fundamental force of nature that attracts 2 bodies with mass. It's the force that keeps us grounded on Earth and governs the motion of planets, stars, and galaxies. Anti-gravity, on the other hand, is a hypothetical concept of a force that repels instead of attracts. It's not a recognized concept in standard physics as we understand it, but it often appears in science fiction and speculative science, suggesting a mechanism to counteract gravity. Third, dark energy. This is a term used in cosmology to describe a mysterious force that is causing the universe's expansion to accelerate. Dark energy constitutes a significant portion of the total mass energy content of the universe. Its nature is one of the biggest unsolved mysteries in modern astrophysics. It's not something that can be directly observed, rather, its existence and properties are inferred from its effects on the universe's expansion and on the growth of large-scale structures in the universe. And finally, extra dimensions. In physics, dimensions are the measurable extents of a space or object. While we're familiar with the 3 spatial dimensions and 1 time dimension, some advanced theoretical models like string theory propose the existence of additional spatial dimensions beyond our perceptible 3. These extra dimensions are usually thought to be compactified or rolled up at scales so small that they're not observable at human or even current technological scales. Each of these concepts represents cutting-edge research areas in physics, often intersecting with theoretical physics, cosmology, and astrophysics. They push the boundaries of our understanding of the universe and are active areas of research and debate in the scientific community. Space-time altered. Imagine a flat sheet representing space-time. Now imagine placing a heavy object on that sheet. You'll notice that the sheet dips around the object, creating a curve. This is a simplified representation of how mass and energy distort space-time. These distortions create what we know as gravity. In space-time altered regions, these distortions are far more pronounced, potentially leading to fascinating phenomena like wormholes, black holes, and time dilation. Gravity, a fundamental force, has always intrigued us. Gravity, as we all know, is the force that keeps us grounded. It's the invisible tether that keeps our feet firmly planted on the Earth, and our Earth in a stable orbit around the Sun. It's the universal force of attraction that exists between any 2 masses, any 2 bodies, any 2 particles. It's what gives weight to physical objects and causes them to fall to the ground when dropped. Gravity is considered the weakest of the 4 fundamental forces of nature. The 4 fundamental forces are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Among these, gravity is so weak that it's negligible in particle physics experiments, despite being the most apparent force in our daily lives. To put this into perspective, electromagnetism is the force responsible for the interactions between electrically charged particles. It's many orders of magnitude stronger than gravity, which is why a small magnet can pick up a paperclip against the entire Earth's gravitational pull. The weak nuclear force is responsible for radioactive decay and certain types of nuclear reactions. It's much stronger than gravity but acts only at very short distances. The strong nuclear force is the strongest of the 4. It binds protons and neutrons together in the nucleus of an atom and operates at subatomic distances. The exact reason for the relative weakness of gravity compared to the other fundamental forces is a significant question in physics. It's also one of the reasons why unifying gravity with the other 3 forces, in a theory of everything, is a major challenge in theoretical physics. Now let's flip the coin. Imagine a force that could counteract gravity, that could make objects float and drift away rather than fall. This is the realm of anti-gravity. While the term may evoke images of floating cars and gravity-defying superheroes, the reality is far more complex and scientifically intriguing. The concept of anti-gravity has been a topic of scientific debate for quite some time. Some believe it to be purely theoretical, a concept that can exist only in the realm of science fiction. Imagine a spacecraft that doesn't need a rocket's thrust to escape Earth's gravity, but instead uses anti-gravity to simply float away. It would not only drastically reduce the cost of space travel but also open up the cosmos to more extensive exploration. Also imagine the ability to counteract gravity would enable the construction of floating structures. This could lead to the development of floating cities, which would be particularly useful in areas with limited land space or in regions prone to flooding. In architecture, it could allow for innovative designs unconstrained by the need to structurally support the weight of the building. The implications are vast, from creating more efficient transport systems to potentially even allowing us to manipulate space-time itself. However, this is no easy task. Understanding and manipulating a fundamental force of the universe is a monumental challenge. It requires not just a deep understanding of physics and the universe, but also the technology to put that knowledge to use. The understanding of gravity and anti-gravity forces could lead to groundbreaking advancements in aerospace technologies. As we continue to delve deeper into the mysteries of these forces, who knows what we might discover? The possibilities are as limitless as the universe itself. So, here's to the journey into the unknown, to the exploration of the cosmos, and to the future of advanced aerospace technologies. Dark energy, a mysterious and unseen force, is believed to be accelerating the expansion of the universe. Picture this, you're in a cosmic tug of war. On one side, gravity, pulling everything together. On the other side, a mysterious force pushing everything apart. This force is what we call dark energy, and it's winning. Dark energy is a term coined to explain the observed accelerating expansion of the universe. It's like a ghost in the cosmic machine, unseen yet powerful. Despite making up approximately 70% of the total energy in the universe, it remains one of the greatest mysteries in modern physics. Now you might be wondering, how exactly does one study something that can't be seen or touched? Dark energy's elusive nature makes it incredibly difficult to study. It doesn't interact with matter or light in the same way that normal matter does, making it virtually undetectable. Plus, our current understanding of physics doesn't fully explain dark energy's behavior, suggesting that new physics may be needed. The exploration of dark energy could hold the key to understanding the universe's expansion. What if there were more than just 3 dimensions? What if there were up to 10 dimensions? It's a mind-bending territory, an area of study that's been challenging yet enticing to physicists and mathematicians alike. Extra dimensions are essentially additional directions in space, beyond the 3 spatial dimensions, length, width, and height, that we're familiar with. They're not something you can see, touch, or feel, but they could be all around us, influencing the world in ways we can't even imagine. What methods and technologies in theoretical physics and cosmology could potentially be used to detect and study extra dimensions beyond the familiar 3-dimensional space and time? One of the most direct methods to probe extra dimensions is through particle physics experiments, such as those conducted at the Large Hadron Collider, LHC, at CERN. These experiments involve colliding particles at very high energies to see if there are any effects indicative of extra dimensions, such as the production of particles that could exist only in higher dimensional space, or the disappearance of energy and momentum into higher dimensions. Also, the answer may lie in the subtle effects these dimensions may have on our observable universe. For instance, extra dimensions could potentially impact the way gravity works. In our 3-dimensional world, gravity follows certain rules. The gravitational pull between 2 objects decreases as you move further apart. But if there are extra dimensions, gravity might behave differently. If we consider a 4th spatial dimension, for example, gravity might become weaker at short distances and stronger at longer ones. This could potentially explain why gravity is so much weaker than the other fundamental forces in the universe. If extra dimensions do exist and we can learn to manipulate them, we could unlock new technologies that seem like science fiction today. Imagine being able to warp space and time to create shortcuts through the universe, or harnessing the power of gravity to build levitating vehicles. These are the kind of breakthroughs that could be possible if we can tap into the power of extra dimensions. However, it's important to remember that the concept of extra dimensions is still very much theoretical. While there are some models in physics that suggest their existence, we don't have any concrete evidence yet. And it's not just about scientific discovery, it's also about inspiring a sense of wonder and curiosity, about challenging our preconceived notions of what's possible. Thank you for joining us on this journey into the unknown. Stay curious, stay inspired, and one day, we will be able to solve these mysteries of our universe.